Hey everyone, welcome to Anupam Tech. This is your fan guy. Today we'll be learning system design fundamentals. In our previous video, we discovered and learned why do we need system design at the first place. And today, this video will be learning few fundamentals of system design like scalability, consistency, partition, availability, and whatnot. So let's move forward and start with scalability. So we start with why system demands scalability. Before that, first let's try to understand what is scalability. Scalability is a system ability to handle increasing load without dying. So this increasing load could be due to increasing number of users to your website or your backend services. I mean, more requests to your backend services, or it could be a DDoS attack as well. Just kidding. And scalability has two important concept in it. One is your vertical scaling, and the other is horizontal scaling. Vertical scaling is very simple. We scale inward. It means you add more resources and CPU to your existing machines or servers. Horizontal scaling is very simple. We scale out. We try to add more machines in parallel to process the increased number of requests. Let's try to understand this with a very simple analogy. Imagine we have a restaurant which has a seating capacity of 10 people, or you can say it has 5 tables where total 10 people can sit, and it can manage up to 50 customers per hour. And for this, you have one main chef, Coco, and two waiters for this particular restaurant. So this configuration works fine if we have around 50 customers per hour. But let's say your restaurant goes viral, and now your restaurant is receiving like 100 to 200 customers per hour, which is now very difficult to manage because with these resources like one chef and two waiters, it's very difficult to manage, right? So the idea is simple. Pause the video and think what we can do here. Okay, so we have two options. One option is to get a bigger kitchen, right? You increase the size of the kitchen, right? Which essentially means you scale vertically. I mean, within the same restaurant, you're trying to buy a bigger kitchen. Or maybe hire a super chef as in hire a chef which has more experience, which can actually manage more, which can actually make more number of dishes within a period of time, right? Which essentially is upgrading your existing resources. Or the other option is you have more number of shifts. I mean, you increase the number of shifts and increase the number of waiters as well to manage the orders, right? You add more chefs. Also, you can open more branches of your restaurant. Let's say you can add 2 to 3 more branches within that area so that the traffic, the footfall is not distributed. So this is how modern system scales, right? You either scale vertically or you either scale horizontally. Now let's discuss the second topic, which is availability. Also, before we start high availability concepts, let's discuss another important aspect in scalability, which is called elasticity. So, elasticity is the ability of the system to scale automatically. For example, for any e-commerce website or any quick commerce website during IPL or during your Black Friday sales or even during a big billion days on Flipkart, you would see tremendous amount of requests and users trying to access the website and ordering at the same time. So we want the resources to increase automatically, and this is how modern system actually work. I mean, you configure them so that they can grow and shrink automatically. You don't need to always kick in and scale manually, either scale vertically or scaling horizontally. So this is how we introduce elasticity in your system. Now let's move to the next topic, which is availability. So we ask this question ourselves: can user access the system when they need it? A very simple analogy would be an ATM. Imagine an ATM which works 24/7. If it works 24/7, the availability is very high, right? It is always available to you. Whenever you step in, you can cache in cache. And if it goes down every weekend, let's say sometime during a day, the availability is poor, which is our typical Indian ATMs, right? And we know the availability is very poor for those ATMs. That means anything which is always available is called high availability, and something which is available but not all the time is called low availability. And for the availability formula is now is very simple. It's total uptime divided by the total time this has been up. Now let's look into some availability numbers, and these are very popular spoken number during your interview, your system design interview, and you call it 29, 39, 49, and 59 availability. When we say 29 availability, I mean the 9 number is appearing twice. So it is called 29 availability, which relates to, I mean, 99% availability, which relates to that the system can experience a downtime of roughly 3.5 days for an year, like per year. And this is how much 99% availability means, that over a year in 365 days, 3.65 days, my system is unavailable. It could be due to maintenance, it could be due to any attack on the system, or it could be due to any failure, any internal failure, or anything. And when we say 3.9 availability, which is like 99.9%, it's 8.7 hour, and simultaneously we have 4 nines and 5 nines. And typically, modern systems like AWS architecture, Google Cloud, and most of the top tech companies, they offer 5.9 and 4.9 availability. And to maintain this availability, it takes a hard, I mean, it takes a lot. I mean, your system has to be very reliable so that it is available up to 99.999% of the time, which is like roughly you have a bucket of just 5 minutes to go unavailable. But it is very unrealistic. You must have already heard of that some AWS services are down. I mean, we had very recent news, right? Where also last year GCP was down for 2 to 3 hours. We try to keep our availability bucket SLO to the point. And also there are some other concepts within it, like high availability. I mean, when we say our system should be highly available, or it should be highly availability, it means simply means the system should survive the failures. I mean, the like even if one server dies, users shouldn't be, you should be noticing it, right? I mean, let's say you have 10 servers and one of them dies due to, let's say, out of memory issue. The user experience should degrade. It should be, the user should be still able to interact with their websites or servers. And then the second concept is failover. Failover is like automatically switching. Let's say your one of your primary DB, which handles all the writes, dies. Let's say your primary DB crashes. So your replica should be automatically promoted to primary, and so that we have some failover mechanism. And similarly, we have RTO and RPO. RTO is like recovery time objective, like how quickly your system can recover, let's say within 5 minutes or 10 minutes. Let's say your system dies. We have some RTO setup so that we can quickly recover a system. I can spin up more machines or redo the stuff so that our systems are back in place. And then we have RPO, which is point, recovery point objective, which is like how much data loss is acceptable. Example, let's say 30 seconds, 1 hour, 20 minutes. I mean, if the system goes down, how much we are fine with the data loss. And these terminologies are quite popular when you do interview system design discussions. So interviewers love RTO and RPO sort of discussion if you are discussing systems which demands high availability. Now let's discuss the third topic, which is consistency. And another very, very important concept, which simply means that all user sees the same data. Now, imagine you have a Google Doc. You type hello, and your friend, the other person who is viewing this doc, immediately sees hello. This is called strong consistency. So now we know that consistency simply means all users sees the same data, but we are not. So this has some hidden. This definition has some hidden gap in it, right? All users see same data, but at the same time, or is it fine to see the same data after some particular interval of time? So when we say strong consistency, that means we want the data to be same as soon as the data is available. I mean, as soon as there's a change in the data, it should be available to all the system, to all the user. Let's say I made a profile pic change. As soon as I made the change, everyone should be able to see my new profile picture. Or let's say, imagine Instagram, you uploaded a photo. Your friend sees it, let's say 2 to 3 seconds later, which is called eventual consistency, and we are fine with it. And some common examples of strong consistency and eventual consistency is strong consistency like your bank database. Let's say you added 10 rupees to your bank account, and at the same time you want to pay after getting added 10 rupees, you want to pay it someone, like you pay 10 rupees. If the data is not available in your database, then that 10 rupees transaction, when you will try to pay, if it is not available, the system is inconsistent, right? And the same dimensional consistency, like we say we are fine. We are fine with if the data is not available as soon as it was made. I mean, it was in the database. Okay, so now discuss why this consistency become hard to solve or hard to discuss during an interview or in your system design concepts. So let's say you have a primary database and you have multiple replicas of it. Let's say you have two replica of your primary database, right? Let's imagine your primary database. This database holds the number of followers you have on your LinkedIn. Let's say I have around 70K followers. So just recently, just after watching this video, let's say 1,000 folks went ahead and subscribed me. Now my primary database has around 70K followers, but my read replica still has 69K. I mean both. So this creates consistency gap, right? I mean, your primary database has more. I mean, the most recent number of followers, but your replica databases, which are like snapshots of your primary database, has less number of followers. So, which answer should user see? I mean, whether it should see 69 or 70, that depends the choice of consistency that we want to our system have. I mean, if we are fine with eventual consistency, we'll say no harm in seeing 69K because nothing will change. I mean, this is not like a P0 thing that we want it right away. It's not like a bank architecture or banking system where you want the data should be available as soon as the transaction was made. So it's fine. So definitely this comes with a consistency challenges. I mean, we might see multiple consistency, but you have to come up and understand whether this system demands strong consistency or it demands eventual consistency. I mean, if it is fine to have eventual consistency. Okay. So also let's also discuss other consistency level other than the strong consistency and eventual consistency. And these two are very important terminologies. And you might be hearing a lot from your senior engineers or during system design discussion in your team. Some other consistency levels are like casual consistency. It is simply like cause and effect, which is like you preserve the order. For example, is comment appears after post. I mean, I know, but this is like very popular. I mean, it should be not before. I mean, let's say the data is available, you should not populate comments even before the post is available. I know it's a very vague example, but yeah. And the other is like read your rights. And believe me, this is very common. I mean, you might even have noticed this. User sees their own updates immediately, and but the other side of the folks see it in later point of time, which is which gives a sense of that feeling uh, to the person who is posting that his post is available, but actually it is like eventual consistency. It comes after certain period of time, let's say 2 seconds, 3 seconds, 5 seconds. But it is very common in large systems like Google, like Facebook, Meta. I mean, they whenever you tweet something, you immediately see in your feed, right? You post, let's say you post something on LinkedIn, it directly comes on the top of your feed. But it takes some time to propagate. I mean, it takes time to fan out to others' feed, right? So that's why it says read your rights. Okay. So now let's discuss the another very important concept, throughput and latency. The bandwidth we'll discuss it later, but as you can see in this image, this picture, you might have already understand what is latency and what is throughput. If not, let's see. Let's see what is latency first. So latency simply means how much time does a request take, like end to end. let's say you made some search request and it takes 100 milliseconds. I mean, you as soon as you hit enter on Google search for a particular query, and as soon, I mean, by the time you receive the output, it's the latency of that particular request. So let's say if it is 100, the latency, we say the latency of this request was 100. And what is throughput? So throughput simply means how many requests was processed per second. Let's say at the same time when you were querying, how many concurrent users were also doing the same thing. I mean, how many requests was getting processed per second. So let's say if it was 10,000 queries per second, so we say throughput is 10k QPS, which is queries per second. Okay. Also, I want to throw some analogy on it, which is like, let's consider a restaurant, right? I love it. I mean, the restaurant analogy fits in almost every system design concept. So in restaurant, the latency is simply how much time the customer waits for getting his order, and the throughput is how many orders restaurant is serving at that time. Let's say if order wait time is like 5 minutes, it's the latency. I mean, I'll receive the order after 5 minutes. You might be seeing on the display board, right? We will see your orders getting prepared, and it like expected time is like 4 minutes, 3 minutes. It gets reducing. I mean, overall, let's say it's 5 minutes, and the throughput is how many number of orders are listed there. I mean, how many orders the restaurant is serving at the same time. Let's say it could be it is serving, let's say, 100 customers per hour. Okay. Now comes the very important concept. It's called latency matrices, and you must be hearing a lot about this term, like what is a P50, what's P90, what's P99 for this particular API during observability. I mean, in a company, you might be dealing with these numbers a lot of the time. So let's discuss this. So these terms are typically used to describe latency matrices, how long it takes for a system or the service to respond to that request. And so these numbers are like P50, P75, P90, P95, P99, and it refers to the percentile. I mean, P50 percentile 50, P75 percentile 75. And believe me, this gives you better sense of how response time are distributed in a typical system. I mean, in typical distributed environment. So let's discuss P50. P50 like 50th percentile, and this is a medium. Yeah, it's a medium. Half the people get their food faster than this. I mean, again, this is analogy. I want to keep it here. So then half the people get their food faster than this, and half the people wait longer than it. Example is very simple. Let's say out of 100 customers, 50 people got their food in less than this time. Let's say 1 minute. So let's say if I say for any particular API, P50 is 1 second, it means 50% of the user had the response time less than 1 second, and the 50% had to wait more than 1 second. And we still don't know about that. And we still don't know the upper boundary, right? We know that lower boundary, that is that 50% were less than 1 second, and the rest 50% of the people, we don't know the upper bound, but they were definitely above 1 second. So let's say P50 is 15 minutes, it means half of the order were served within 15 minutes or less. Now, let's consider P75. This is the point where like 75% of the people got their food faster than this particular time, and so 25% of the people had to wait for more than 20 minutes. And again, this gives again a better idea, like what is the distribution, right? And then P99, like P99 is like very important metrics, and we also call it tail latency because it is like we now have more confidence when we say our API. Let's say get food in a restaurant, get food API P99 is, let's say, 5 second, 5 second, or let's say 40 minutes. P99 is, let's say, 40 minutes. Let's give some realistic number. So that says if P99 is 40 minutes, it means 99% of the customer receives their order in less than 40 minutes, and only 1% people had to wait longer than this, right? And this sets a clear picture of a system how well it is performing, and it is very critical in large system like distributed large systems. That's why this tell P99 tells that yeah, most users are happy. Some users are like miserable. Like 1% people had to wait more than 40 minutes. And this P99 most of the time reveals the critical issues, like hidden critical issues within a system. And this is very popular also. We call it the tail at scale problem. Right? It's a very famous concept. Because this 1% request, with this 1% request, you'll study and you'll get to know what is going wrong in your system that you need to fix. Perfect. Let's move forward. And then this question come, why latency metrics are useful? One asks, okay, I know you have must have got enough idea, but again I want to continue on this. If you look at P99, you see that there is a small group of people who experience much longer wait time. And in a system design context, that means a few user might experience worse latency than most of the others. And you might need to work on improving the system for that small group. And we discussed just now. Whereas P50 and like P75 are often used to how the majority of the users experience, like 50% and 75%. Perfect. And then there's a very important concept called little loss, right? Let's try to understand why this little loss exists. Okay. Now imagine you're running a payment service, and uh, like 1,000 requests are running every single. The QPS is 1K requests per second, and let's say each request takes 2 seconds to process. I mean 2 seconds to complete. Like latency is 2 seconds. So now when a natural question can come to you is like, Alibab, how much how much, or maybe let's say how many requests are sitting inside the system right now? And if you are like senior engineer, or let's say SD2, you know this, we are talking about what are my in-flight requests. What is the number of the in-flight request? And one might ask, Anwar, why this is important? I mean, why do I care how many requests currently my server is dealing with, right? This matters because every request comes with a cost, right? Because it consumes your CPU, some part of your CPU. It consumes some part of your memory. It consumes your threads, your active threads. It takes it takes a hit on your DB connections. So if too many requests are in parallel waiting to be executed or getting executed, this tells the probability that your system might be under a load, or it might crash as well. So to calculate this number, the math's very simple. We just multiply the throughput and the latency, and you get your number of requests that are in flight or sitting in the system right now. Suppose you have 5,000 requests arriving per second, and the average latency, let's say 200 milliseconds. Now it's like 0.2 second. Your concurrency, I mean, this ultimately concurrency is like you multiply and you get like 1,000 requests are actually being processed at that moment. At that same point when there was 5,000 requests on a latency of 0.2 second, and let's consider this was like P99 latency. This was P99 latency, and I can roughly and estimately say 1,000 requests are being processed, and this immediately tells us that how many threads might be needed to process this many requests. I mean, we asked this question before actually designing the system or designing the API. We asked the interviewer how much QPS is expected, and then we can do the reverse engineering and understand how many active threads are needed. That will tell you how many CPU cores are required, and also this will give you enough idea on how many DB connections we might need to open, and also memory requirement. But memory is cheap. Okay, the last topic of this video, which is partition. Okay, let's talk about partitions. Partitions are very important. I mean, I believe it's one of the most important concept in distributions. It's in distributed system, and you will know it even better when we'll be learning cap theorem and Packel theorem in the next video. But also, let's learn what is a partition. So a partition, like a network partition, can occur when a system, when two systems are not communicating. I mean, both the system might be live, but they are not connected. Let's say you have your Mumbai data center. Let's say your cloud, or let's say or let's simply assume you have two data centers. One is like in Mumbai and one is like in Delhi. They usually communicate with each other. They're working fine, but on a random day, the network pipeline got broken, or the let's say cables were cut. Now both systems are alive. There's no problem in the data center, but the connectivity has lost. Let's say what can happen in the worst case. I mean, this is partition. I mean, the 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 connection is broken now, right? Neither can talk, but they both still are alive. Only the network is broken. And when we say Anubhav, okay, why it is so important? I mean, yeah, they both are not connected, but they are still working, right? I mean, they both can serve the traffic. But no, I mean, they might say, oh, yes, servers are alive, like communication work, right? No, but in reality, network failure leads to majority problem. I mean, I know. I mean, you can say network failure happens really, but your system should be resilient. It should be reliable. It should be reliable to partition, and this gives birth to a very important concept, a very important concept of cap theorem. I mean, the system should be tolerant to partition. Okay. Let's also talk about latency versus partition, which is again will give more idea to you. So let's say a slow network often looks like a partition, right? Let's say uh, your request for, let's say, you're trying to listen a song on YouTube Music, and you're requesting a song, and it's taking some time to start, right? You might say it's either this internet could be slow, and you, as a system design perspective, you might think there's some partition, right? The servers are disconnected maybe, and distributed system must choose when this thing comes, we must choose either to wait longer or to fail fast. I mean, in such situations where various systems are unresponsive because there's some partition, or let's say there's some brokerage between the two servers, one might say there's a design choice. Either you have to wait longer, we'll wait for, let's say, 10 minutes, which is not realistic. But yeah, let's say we'll wait for 10 seconds. Or we'll fail fast and say it's a failure. And we'll say, let's say, not found, that let's say a song was not found, or the servers are not reachable. And this decision derives the cap theorem, which is like very, very important. And we'll be learning about this cap theorem because this is like this lays the foundation of your design choices. I mean, all the non-functional requirement that you will be gathering during a system design interview is based on cap theorem. And we learn also the advanced version of cap theorem, which is like Packel theorem. I mean, cap theorem talks about consistency, availability, and partition, and it says in real life you will be never compromising on partition. So your system should always work despite of network partition, right? It should be partition tolerant. So we always keep the P and always negotiate between consistency and availability. So it says you can either have consistency with partition tolerance or availability with partition tolerance. You can't have consistency and availability together compromising partition tolerance. No, you can't have, because we just discussed, right? If your two centers are not connected, you can't guarantee consistency because these two data centers might have different data because they are not connected to each other. Or also you can't guarantee availability at the same time because your system is not irresponsible. It is itself failed to communicate. So that's why we never. I mean, we'll talk a lot about on this in the next video. Also, if you're liking the discussion, or if you see anything that is missing, or if you feel that Anubhav, if this thing was available in the video, if you have explained this way, or if you have given more examples, or if you have given more visuals, I would love to see that feedback. Please put in this comments. And believe me, a lot more quality content is planned and will be posted soon. Please like, share, subscribe, and hit that hype button so that I also get motivated and bring up with more advanced concepts in system design and make your system design into feel like easy peasy, like crazy. Chalo, see you. Bye bye.